Oh, thanks. That's wonderful, wonderful. Thank you. Deux fois, c'est impossible.
Okay, so for the second talk of the morning, we have François Thilmany, who's going to speak about Prasad volume formula and applications.
Thanks, Brian, for the introduction. So I'd like to obviously thank the speakers for inviting, the organizers for inviting me to speak, and also for doing a wonderful job at organizing the conference. It's my first time in India, and I had a great time, so I will for sure come back if I get the chance. What I want to tell you about today is Prasad's volume formula. So it's a volume formula for arithmetic quotients of semi-simple groups that Prasad developed in the, even a bit before the early 90s. And that's extremely useful. So the main point is that this formula you can really use to compute volumes. And in fact, we will. So I want to tell you a bit about what was done earlier and also the motivation for coming up with such an explicit formula. I will write down the formula in, let's say, the standard arithmetic case, and explain what goes on in there. So explain a bit what the factors that appear and how to manipulate them. Then I want to say a word about applications, namely to classification of fake projective planes and some results in hyperbolic geometry. And then I want to talk a bit about my own work on lattices of minimal covolume in a cylinder. So let's start. So the first maybe results. So first, early results or formula for volumes is due to Siegel. This dates back a long while ago. And so he proved that for his normalization of the volume of this quotient is precisely the following product of values of zeta functions. This is quite a nice result. So I should say really quickly, so I don't tell you the normalization here, it's because I will change it later. I will tell you the normalization we will use later. It will be slightly different, and you will be able to tell the difference later on. So this is a nice result. The only sad thing about it, it really only works for SLN Z in SLN R. Right? So what we're aiming for is to get something similar, but for every S arithmetic group in the Lie group. So here's maybe another result due to Borel. So he gave a formula a bit more general. The following formula. So let me try to write it down. So I will tell you what's in the formula in a second. So Borel gave the formula for the volume of the quotient of G mod gamma, where so G is SL1 of this algebra, and here A is a division algebra. A is a quaternion algebra, so also yeah. Over K some number field. So in this setting, he gave this formula for the volume. So there's a constant factor in front. I will tell you exactly what the numbers are in a second. This constant then shows up the discriminant of the number field K, then shows up a special value of the zeta function of K, and then a product of local factors of this form, so the norm of a prime ideal of OK, And which primes do you have to take? You have to exactly take the primes for which A ramifies over KP. So now what are these numbers? So this group you can decompose, right? So it turns out that depending on how A splits at the Archimedean places, you get a bunch of different factors. So you get a couple of factors of SL2, A many of them, some factors of SL2C, B many of them, and then I don't have space. Then let me write it like this. Sorry. A couple of factors of the compact standard unitary group, C many of them. So you decompose this group, G, you get these invariants A, B, C, and then associated to A, you also have invariants, so coming from the base, the field of definition, and coming from the ramification. You put these invariants together, you get the volume of the quotient. So this is wonderful. And Prasad's volume formula, in fact, is a straight up generalization of this, which will work for any group. So this I want to state later on, but I wanted to give you a bit of a historical perspective. So I wasn't there at the time, but Gopal told me that the motivation, in fact, one of the motivations to develop his volume formula came from a question of Tits. So Tits asked if, so he was working on buildings, and with I think Cantor and Lieber, they had a theorem that said that there are basically only finitely many chamber transitive actions on Brugger-Tits buildings. And Tits asked if there is something maybe similar in the case of quotients G mod gamma. Sorry? So I think they were working on chamber transitive, and then I will talk about vertex transitivity also as an application. So indeed, Gopal and Borel managed to prove such a theorem. So I will write this theorem down, and to prove this theorem, the key ingredient is a volume formula. So here's the theorem. Maybe before I have to tell you a bit of the setup, perhaps. Just at least I need to tell you how to normalize the measure. So this is actually a key fact. So let's take K to be a number field. And then I give you G, an absolutely simple group. So in particular, for every place, no, for the finiteness, I don't think you, but yeah. So I need to tell you, so how to normalize the measure at each place, right? So for each place of K, we have this group GKV, and we will normalize, so the measure mu V on this group GKV, such that, so I want mu V to give measure 1, 2, so 2 cases. The stabilizer of a chamber in the building. This is if V is non-Archimedean. And otherwise, I wanted to give measure 1 to a maximal compact, any maximal compact subgroup of the following group. So you take G, look at the restriction of scalars from AV R of G. Take the C points. Inside of there is a maximal compact, and you just have to ensure that this is 1. So this is a good normalization, for instance, because when you compute these volumes, often you have to deal with a lot of compact factors in the group, and this is convenient. It makes your measure 1, so it makes the volume formula very robust. And it's necessary to have a robust normalization, of course, because as we will see, the forms that give different lattices can become more and more complicated. And if you don't normalize the measure in a sensible way, the theorem I'm going to write down makes no sense, right? So this is necessary. I'm sorry, what? This is a C. Yeah, this is a complex numbers. So G is a group. G is a group over K, right? So this is the restriction from KV to R. That's R group. I plug in C points. C is a R algebraic, and this is allowed. Right. So this measure you have to understand. I'm not going to go into the details, but this measure is a measure on GKV. And you want to normalize it so that when you induce the measure on here, you get 1 on the maximal compact subgroup of this group. So this measure is on G. So if you want. I'm just picking a scalar, right? It's okay, so here's the theorem. It says the following thing. So given a bound C positive, there are only finitely many choices of a number field K a group G as above, namely absolutely simple. And I want to impose a rank condition of absolute rank at least 2. A finite set of places. Let me call them S, containing all the Archimedean places. And then an S arithmetic lattice. Let's call it gamma. This lies inside GS, which is just the product of all the S points. Such that, so here's the key thing. The volume for this normalization of the measure, so this, maybe I should write it here. It's the product. The local measures. Such that the measure of the quotient is bounded by this bound that we took at the beginning of the theorem. So this is a striking finiteness theorem, right? So there were finiteness theorems akin known for a fixed group. So for instance, Wang had a theorem that said that there were only finitely many conjugacy classes in non-badly behaved groups below, with volume below a certain bound, but this is a uniform overall group. So you give yourself a bound on the volume, and provided you don't mess up the normalization, there are only finitely many choices of even groups and fields and places that reach this bound. So to prove this theorem, it was crucial to have a very tight understanding of the volume, and this is provided to us by Gopal's volume formula, which I want to state now. So before writing down the formula, I will need to tell you what the formula applies to. So the formula applies to what Gopal calls principal arithmetic subgroups, and I will tell you right now how to build them. So I need to remind you of one thing from number theory. So associated to this number field K, so we have a ring of Adels. So this ring of Adels, it's a restricted topological product of all the completions of K. So it's a nice object that packages at the same time all the completions of K. So it's restricted with respect to this family of compact subgroups, namely the ring of integers for non-Archimedean places. So the nice thing about this ring of Adels is that so it contains K. So K is embedded diagonally. and its image is discrete. And then it also contains, and this was the point, all the completions. So this this is a continuous. It's all right. So this is a continuous map, and AK is locally compact. All right. So now with this, what I can do is so now I have a global object which takes which has in it all the different completions. So I can use this to kind of encode all local information at once. So I will do this in the following way. So I will tell you that a family, maybe I should, yeah. Family, so PV of subgroups of the GKV. I call it coherent. So let me tell you which subgroups. So we take parahoric subgroups. So this means they stabilize some facet in the building. So Brian told us about the building. This word just means that this subgroup PV is the stabilizer of a facet in the Briatis building of this group. So I see that this family is coherent if the product of these groups, this is open in the finite LLs, but maybe write it like this. So if I give you all the Archimedean places, this is open in. What this means is that these conditions that you're imposing locally can actually be satisfied at the same time. This is rough intuition for this. So in fact, with the next thing we will do is try to satisfy them at the same time. So given such a family, so I can define a principal yeah, it's just, yeah, it ends up being, I mean, the reductive model has to be well chosen. It's one associated to the correct parahoric in the tail. That's right. Yeah. So the principal arithmetic associated to this family is the following. So I call it lambda, function of the PV, and it's just literally you take all the elements of GK that satisfy these local conditions. So let me write it this way. So if you embed GK diagonally in the Adels, what you're asking is no conditions at the Archimedean place, and at the non-Archimedean place, V exactly the condition imposed by P. Okay, so this is the setup I want. So it turns out that, so here's the fact. So if so if you construct a lambda like this will be, so this is a lattice in this group G infinity, which remember was just the product over all the infinite places of the KV. So I've said it already, but I will recall it. So we will normalize the Haar measure, mu V on GKV as before. And then I will also set mu A to be the induced measure on the Adel group, which is all the places at the same time. And then let's say mu infinity. This is the induced measure on this group G infinity. Okay. So with this, let me write down the volume formula. Here's the theorem. Sure. Yeah, this is a bad idea, yeah, because it doesn't converge. Yeah, sure. Yeah. That's right. Yeah, that's right. Correct. I'll come back to that in a minute. So I won't need it. So yeah, that's right. So the problem with this is that the normalization we took gives measure 1 to the stabilizer of a chamber. And what you want, if you want to write something like that, is gives measure 1 to the stabilizer of a hyperspecial parahoric, of a hyperspecial vertex. Okay, I won't need it because I will only compute U infinity. So now I need G to be simply connected. So there's a technical assumption. Let G be almost simple. Absolutely. And simply connected. And then I give you, as before, a coherent family of parahorics. Which, if you use them as local constraint, allow you to construct this arithmetic group. And this is the one that we will compute the volume of. So here's the formula. So then the covolume of lambda has the following expression. So it's equal to, I will write down a bunch of number theoretical concepts, and then I will explain everything that goes in the formula. So there's one discriminant, the norm of a relative discriminant. And then here I have a big product. I will tell you what the MIs are in a second. So it's raised to the degree of K over Q. And then probably the most important thing, these local factors, which depend. So this is the only factor in the formula that depends on the local constraints. So we have one for each finite place. And I will tell you what they are in a second. So this is a measure we use to normalize. So this is the absolute discriminant. This is the norm of the relative discriminant. This here, let me call this V and inverse. This is the inverse volume of some balls in Euclidean space in these dimensions. So the inverse of this. So this, you know, this is the degree. This guy here, this is just some invariant. So invariant. So depending only, in fact, so it depends on G, but it only depends on the quasi-split inner form. So let me write it very briefly. Depending only. Quasi-split form of G. And then you have these local factors. So I will write down an expression for the local factors immediately. So they are given as follows. So you remember from Brian's talk, this guy was a stabilizer of a facet in the building. And we had a group scheme associated with it. This was the whole point of Brouillat's theory. So I'm going to use this group scheme, I tell you in a minute how, to get some numbers, and these numbers will give you the value of these local factors. So it's given as follows. I will tell you what the letters mean in just 1 second. So some power of the size of the residue field to some dimensions, which I tell you in a second, divided by the size of a finite group, and the finite group is the same as the one in the numerator. So what is this? So this guy, M, and also this guy, this is the reduction of, let me abuse notation, so of the scheme associated to PV to the residue field FV. So FV is the residue field of K at V. This is my parahoric. I reduce it. I get a finite group over this finite field. This is the group. This is the size of the field. Oh, yes, correct. Yeah, yes. So, yeah. So you have to be a bit careful. So as we've seen in Brian's talk, when you do this, you don't always get a reductive proof. So what I want is I want to kill the unipotent radical and only take the reductive quotient. So I will write it down here. So reduction of this modulo unipotent radical. Exactly. Thank you. I didn't tell you what curly M is. I will just say it out loud. It's the exact same thing as M, but for the quasi-split inner form of G. So you look at the quasi-split inner form of G, and then you have to choose some parahorics correctly for this guy. And with the correct choice of parahorics, you do the same thing for this. So in the case, the nicest cases where these parahorics are, let's say, hyperspecial, and the group is to begin with quasi-split, and then they're the same. So sorry. No, it's a Q. Yeah, it's a Q. Yeah, this is fine. No, that's it. That's it. Yeah. All right. So I'm sorry. What's an integer? Yes. S is some integer. It's depending, if I remember correctly, quadratically on the rank of G. So it's some quadratic function of the rank of G. So it grows with the rank of G, and the dimension also grows with the rank of G. Okay. So which N? This? L. Ah, yes. I didn't tell you what L was. So L is the splitting field of the quasi-split inner form of the G. So behind this, so to understand this guy, and this guy, you need to know what the quasi-split inner form of G is. So this is, I'm not going to go too much into detail because there's no point. All my groups will be quasi-split and we won't need it, but that's right. Well, if you care about the specific group, you can always come to me and maybe we can work out the quasi-split inner form. But for now, I would just want to run an example to see exactly. So this looks like abstract nonsense. And in particular, if you can't compute this, you can't compute anything. But it turns out it's not, and you can compute all these things. And I will do it in front of you for SLN. So let's do G, which is quasi-split. So it's equal to its quasi-split inner form. And I just take it to be SLN over Q, the easiest case. My number 4. And then I need to tell you what parahorics I choose, right? So let's take the easiest ones. So let me take PV, which is be SL and ZV. So in the building of SLN, every vertex has the same role. I'm taking the stabilizer of a vertex. Those are the best parahorics in this case. So that's what I'm taking. So if I take all these constraints together, what is the principal arithmetic subgroup I get? This is rather straightforward. So this is what? This is the set of elements of GQ, which lie in all of these, place by place. But this you know, right, from basic number theory, that if you're V integral at every place of Q, then you're actually just integral. So this is precisely GZ, which in this case is just. Okay. And then we can compute, let's maybe first compute the local factors and then put everything in the formula. So the local factors are what? So for PV, the local factor I have is the following. So I have, in this case, M and curly M are the same. I'm giving you this. So the dimension is just n squared minus 1 over 2. So I have QV to this power. And then downstairs, I have the order of this finite group. So it turns out that I chose the parahorics very nicely. There is no unipotent radical in this case. No need to take a quotient. And this is just SLN over the finite field F V. So let me write down so if the order of the field is QV, then the order of the group you get downstairs is the following. So you get this product. Because there was a half here. Yes, you're right. Yes. So this is almost the order. This is the order of a GLN, and if I want the order of SLN, I have to throw in the numerator. So now it turns out that the power here is exactly the correct power to do the following simplification. So I will divide both numerator and denominator by this power, and I will tell you what I get. So what I get is the following. So this will simplify with this after simplifying the correct number of powers, and the other remaining factors are the following. So you get 1 over 1 minus the same power times, and then the last term, which is not this one, is the one before, you will get 1 minus 1 over v squared. So the power 1 disappeared because it cancels with this. This is actually crucial. So maybe this you recognize. This is precisely the local factor of the Riemann zeta function at v for 2 up to n. So if you put them together, what do I have? So K is Q, so no discriminant. It's quasi-split, so no discriminant. This is one copy, so the degree is one copy of the volume of some balls in some dimension. So let me just write it Vn. And then just the product of the local factors. But the product of the local factors of the zeta function is just the value of the zeta function. So this is again exactly what appeared in Seeger's formula. So the product of these special values of this volume. And so up to this factor of V that we actually had to introduce to make it robust, you get exactly back Seeger's formula. So I've given you the simplest possible example, just SLNZ in SLNR. But if you know a bit about algebraic groups, you can actually work quite well with this formula. You just have to know what to put in, in these invariants and manipulate the group G a bit, but it's not so bad. And so people have done this. People have used this extensively, and I will tell you now a few results as much as I have time for. Here are some applications. So the first one is two fake projective planes. So remember that, so those are, just as a reminder, those are smooth, compact, complex surfaces. So this is so far saying not much, but so the key thing is that they have the same Betti numbers. As the true projective plane, namely this guy. Okay, so I guess you maybe want to exclude. So some people, I don't know if you call this a fake projective plane. This is the true projective plane, and the ones that aren't this one but have the same Betti numbers are the fake projective ones. And so here's a key fact that allows so far we only have geometry. So this fact will allow us to leverage the volume formula to say something. So it was proven by Klinger and independently Young. They proved that fake projective planes arise. So fake planes arise as arithmetic quotients of the symmetric space. So let's say of X. This is the symmetric space of PU21, the sign 2-1 R form of PU by torsion-free. Okay, this is what they shown. So there's the arithmetic quotient, and in fact, we give a name to the lattice of this by some gamma. This gamma, the point is that it's arithmetic. And in fact, so if for it to be co-compact, it should be uniform. And for it to be smooth, it should be torsion-free. So this is kind of the setup we're looking at. And then we also know from the Betti number, not necessarily. Yeah, not necessarily. Just torsion-free arithmetic lattices. The thing that we do have, the strongest condition that we have yet to impose is what does the Betti number tell us? So the Betti number forces the Euler characteristic, which in turn by Gauss-Bonnet forces the volume. So this is with some fixed, given fixed, either Euler characteristic or volume. Exactly. And then the volume, depending on the normalization, is 3 times this V, I guess. It applies. That's right. So I make a comment about this. That's correct. That's correct. Well, I'll make a comment just after writing the statement. So here's the theorem that Prasad and Young showed. So they classified. So Prasad and Young classified the commensurability classes, and then inside each commensurability classes, I think Cartwright and Steger later give the actual detailed list of the different ones, but I will just tell you the number of commensurability classes, and the answer is 28. So there are exactly 28 commensurability classes of big projective planes. Yeah, so Klinger and Young proved that they arise as arithmetic quotients, always. And then the uniform torsion-free and Euler characteristic condition come from the definition. Okay, that's right. So this is key because otherwise you cannot use the volume formula. So as Venki pointed out, actually the way I stated it, you cannot use it straight away, and that's right because there are some subtlety. And the subtlety is precisely that you have to relate this gamma to a lambda that is a principal arithmetic group. And so there you have to compare the commensurability index. So you have to control 2 things. You have to control the co-volume, which you can compute of the principal arithmetic guy, and the index of commensurability with the guy that you started with that may or may not be a congruence subgroup. So both things are subtle. So the volume formula we have, but then you still have to make sense of the factors. So both evaluating the factors, especially the local factors, and controlling the index are quite subtle things. But given the 13 minutes I have left, I won't say much about, but yeah, I'll try. Okay, so here's another quick application. So this time to hyperbolic geometry. So here's a theorem. There are a few theorems of this vein. I will write down one, and then you can ask me for other symmetric spaces. I will gladly tell you. Bello. It is a theorem due to Bello-Lipetsky, and then also, I will write it simply, but so it's one work of his and one work of him with Emery at 2 different times. So they showed together that for every n greater than 4, there is a unique uniform and a unique non-uniform arithmetic subgroup. So let me call it, I guess, gamma n, or maybe gamma uniform, gamma non-uniform, so the isometry group of hyperbolic space, real hyperbolic space. So what's the condition? Of smallest volume. So this is the point. So it's a unique arithmetic subgroup of the of smallest co-volume. And in particular, the orbifold you get as a quotient of hyperbolic space by this guy is the smallest volume, compact, respectively not compact, hyperbolic orbifold in this dimension. So there's some kind of classification of minimal hyperbolic orbifolds. And we know also like what it's defined over. I can tell you. So if it's so it's defined over q root 5 in the uniform case and q in the non-uniform case. Just as a hint, so that you get a bit of the arithmetic flavor. So there are similar. I don't have time to write them down, but there are similar results for quaternionic projective space and complex projective space. They're not complete. There's two problems. Arithmetics get very subtle, and in low n, or sometimes in the co-compact case, it can get tricky. And then the other problem is we don't have arithmeticity. So this is among arithmetic subgroups. One can conjecture, I think it's reasonable to think that these guys are also achieve the minimum among all subgroups, but this is a bit too much to handle at the moment. Let's see. And maybe I can write down one more application. You're asking me if we know the smallest torsion degree. I think not in general. So we know it for small n. So for instance, for SL2. But not in this. I don't think they know. Yeah, if I remember correctly. So it's very subtle because this you have to control understanding where the torsion lies in the group, and then again you have an index of commensurability that you have to compare. So yeah, there are good reasons for why they don't assume it's torsion free, and in particular for fake projective planes, there you want it to be smooth, so you have to deal with this. So Gopal and Young had to deal with this index, and it's quite a bit of work. So here's one more theorem which has a bit of a different flavor. So this is a theorem due to Mohammadi. And Salehi-Golsefidi. It's also some kind of finiteness theorem. But this time about vertex transitive actions in Bogaty's building. So it says the following thing. There are finitely many families, and they give them, so finitely many discrete subgroups. Let me call them gamma. Inside the automorphism group of a Bogaty's building, let me call it B, associated to some group G over some field K. So, such that gamma acts. So I should maybe put a bound on the measure. Let me write it here. So discrete groups of the automorphic group of this building, and this building should have dimension at least 4. In that case, there are only finitely many families acting vertex transitively. On this building. So again, they give the explicit list of families. Let me not write them down. It's a bit complicated to describe, but we have them. That's it. We know exactly, starting at dimension 4, what acts vertex transitively on the Bogaty's building. I should say, so K is of characteristic 0. This is important. And I can tell you now, the last 7 minutes about the last result I want to present. So here's another theorem, which is pretty much the main result of my PhD thesis. And it says the following thing. So if I tell you that n is at least 3, then up to conjugation, SLNZ is a unique lattice of minimal covolume. So you should know the group, right? Because it's super rigid, so I don't need to write it, but okay. This is the group. So I will, in the last 5 minutes, give as well as I can the steps of how you approach this. And I will comment immediately that there's a big overlap, surely on the methods, but also on the style of applying the methods between the steps of proving this theorem, the steps of classifying fake projective planes, and also these kind of minimal volume consideration hyperbolic geometry. It's very much alike. The real subtleties is every time the group changes, and then you have maybe torsion-free, not torsion-free, and every time these changes, these factors a little bit. But the volume formula is quite, I mean, the room for volume is quite tight. And so if you want to get it down to low dimensions, you see every time there's a lower bound on the dimension. The reason is because it gets harder and harder for low dimension, and this is the whole game. The whole game is how far can you push it to understand it. As an example of that this is meaningful, so this theorem actually is not true for n is equal to 2. So this is a classical fact. So observe that. So for n is equal to 2, the lattice of minimal covolume in SL 2R was known. So it was known and proven by Ziegler, also in 1945, I think. That the lattice minimal covolume is conjugates of the 237 triangle group. Inside set 2. Okay, so there is a reason why I couldn't get it down to 2, is just it's false. With this, we have a full classification of the lattices of minimal covolume in all SLNs. And then, as I said, maybe I can say a bit about the proof. What do you have to do? Oh, I shouldn't erase this. I'm sorry, what? It's good. I don't know if it's, I think not, but because if my memory is correct, you may be able to even find an index 2 subgroup of this triangle group that's better than SL2Z. So it's not even as good as a index 2 subgroup of the good guy. So it's, yeah. I don't know exactly what the rank is. I mean, what the podium of the top volumes is. No, it's not known. So what the minimal co-compact uniform lattice is, it's not known. I could make a guess if not in the last 3 minutes of my talk, maybe later. Okay, so yeah, that's for sure. Yeah. Yes. Sure. Among all lattices, even non-arithmetic ones. I will say a minute why there's actually no restriction. So let me sketch the argument. So let me fix. Let gamma be a lattice of minimal covolume in the group that we were looking at. Fix one, and then I'm going to make the others compete for volume. So the first thing to do is so use Margulis arithmeticity. So this implies that so gamma is arithmetic. This is how I get rid of the non-arithmetic ones. And in particular, you can give a form for this guy. So so there will be a K group, which satisfies the so simply connected, absolutely almost simple, such that we have this Archimedean places of G. This surjects, let's say in the first, I can order the components, let's say in the V0 component, this projection in the 0th component. So this goes to SLN R. And gamma is commensurable to the image of GZ. So just from this description, I will quickly write down a few number theoretical consequences. So the first thing is that K should be totally real. So this implies that K is totally real. And we know what the group looks like at all the places. So at KV0 by construction, this is just SL and R. And then at the other places, it should be compact. So it should be this compact form of SU over R. So for this is V in infinite places, but not V naught. Okay, and then you can also say something. So this group, the SLN is quasi-split, but this group G, where is it? This group G may not be. So I will tell you a bit about the splitting field of the quasi-split inner form. So this guy L from the volume formula, we know what it is. So the signature of this guy. So it's a quadratic extension of K, and it has signature. The signature, it's 2 m minus 1, where m is the degree of K over Q. So I don't know if I'm allowed to take back the time that I lost by answering questions during the talk. It's okay. So I'll take 2 more minutes of your time just to use this, because otherwise I'm doing nothing. So this makes sense, right? These 2 places correspond to the places lying over V0 that you should give you a split group, and these guys give you unitary groups, so you better have a Galois involution, so it should be C. This is where this comes from. So it turns out that there's a criterion. So if gamma is minimal covolume, surely this means that gamma must be maximal. If there's a bigger lattice, it will have smaller covolume. And then we have a criterion. So there's a criterion, so Rolf's criterion. This tells us that we can relate, this comes back to Venki's comment, we can relate this gamma to a principal guy. So how? Like this. So gamma is precisely the normalizer in GKV naught, so in this copy of SLN, of lambda, for some lambda, principal arithmetic, associated to this family, let me call it the same name, this family PV of paraorics. And now we're in business, right? So now there's 2 things to do. So the first thing to do is compute the covolume of lambda. So the covolume of lambda, let me call it this. This is given by the volume formula. And then the second thing to control is the discrepancy between lambda and gamma. So we're lucky that the commensurability has actually, in this case, just the index. Lambda is a subgroup of gamma, so it's just the index. So the second thing to control is this index of lambda inside gamma. So this is controlled. I'm going to be very sketchy, but so this actually requires arguably the most work. Once you have the volume formula, this is the next biggest thing. So this is controlled by methods of Borel and Prasad that they've actually already used to prove the finiteness theorem. So it goes back all the way to the finiteness theorem. Very briefly, this bond you can obtain by combining 2 things: the action of gamma on all the Brouatides buildings at all the places, and also some cohomological invariant, namely the Galois cohomology of the center of G. So I will write down the summary. So I just not right there yet. Let me write down the summary of the bonds that you get, and then I will wave my hands, and you have to believe me that you can actually conclude with this. So the bond on the index you get is something like, looks like something like this, so that we have a sense of, there's a class number of this field L that shows up. There is some constant. So this is either 1 or 2, depending on the parity, to the power of the dimension. 1 copy of n. And then, kind of like in Borel's formula, those are degrees of division algebras. Some division algebra. over some set of places. I won't tell you what the set is, but it's some finite set of places that you have to control. And then also, so these guys, so this represents the action of the parametrics of the group on all the local places. And these are the sizes of the stabilizer and the type of the parametric. So it's some geometrical quantity related to the action of G on the building at the place G. This is for all finite places. So this is what goes on in the index. And what goes on in the volume formula, luckily it's still on the board. You have these factors. So if you put them together, so this works in your favor, right? These things tend to grow. The index works against you, right? So you only have sorry, this is not an equality, it's an upper bound. So the index works against you. So you have to bound the things in, if you want to exclude this gamma from being something other than SLN, you have to bound the things in the formula from below and bound these guys from above and combine everything at the same time. So you have to do this simultaneously, right? L shows up here, but it's the same L that shows up in the volume formula. So you really have to control how much index can you gain, what's the cost of gaining index 2 with respect to having to take a horrible form of the group that's not quasi-split, and then you have this discriminant showing up. And so this, I will just say a few names. It requires the classical Minkowski bond, but also improved bonds by Odlisko. For the, you need so for controlling the cohomology that I haven't written down, you need to understand the unit group, you need to understand the regulator. So you need basically bonds for every single number theoretical invariant you've come across. So you have to put them all together, and then it turns out that if you do this very carefully, no lattice can beat SL and Z as long as N is greater than 3. And I will stop here, I think. Taking enough of my time.
Okay, any questions or comments?
Thanks a lot. You've just mentioned that you need Odlisko's bounds.
Yes.
So, okay, so Minkowski gives you a certain bound, and Odlisko is slightly better. So you need 62 or something.
I need yes. So I need Odlisko's bound, and in fact, I really need both because there is a range. So I give a name to these parameters. Yes. So M is the degree of the number field, and N is the size of the matrices. Depending on the values of the pair M N, Minkowski's bond is better or not than Odlisko's bond. And even inside, Odlisko has a whole family of bonds where you can play with parameters. And to get it, so I think if you don't care and you are happy with N greater than 10, you may get away just with Minkowski. If you want to get down to N is equal to 3, you need to even pick the parameters in Odlisko's family of bonds correctly. And different G will give you different discriminants, and the leverage you have is every time different. Every time you have another form of the group, this may be bad, but this may be good, or this may be good, and this may be. So you really have to play with these bonds a lot. So right now, I am not aware of a discriminant bond that's strong enough to avoid doing this. So I really had to use several.
So is it fair to say that when N is large, is very large, it's easier?
Yes, yes, because of this factor chiefly, and in the second range, so this is the thing that grows the fastest. So it has this is M, right, the degree. So this grows the fastest, and in the second rate, this discriminant. Those are the best two, your best friends.
Thank you.
But for so I don't know if it shows, but for instance, if K is Q, this factor is the same for all lattices defined over a group, defined using a group G defined over Q. So this gives you no leverage after you've already proven, let's say, that the trace field of such a lattice has to be Q. Then you lose this leverage and you have to go to the next guy. Then you have, so this guy actually also dies when K is Q. So you don't have this guy, you don't have this guy. You're losing, you're losing leverage as you go in the proof, but you're getting closer to showing it. So that's the whole game. So sometimes this is exactly echoing Gopal's comment. Sometimes you do all this and then you realize, there is possibly like this group that beats my group, but then you realize it's a horrible group and that there's no way you can even come up with a parahoric that's anywhere close to a good volume. And then you have to go in this group and check, what's the structure? Where does it ramify? What can you possibly construct for parahorics? And then realize that actually, you've already lost the game. So, but you have to, so it's not case by case, but sometimes you do have to go deep in the structure of G when you lose the leverage of the other guys. So it's the whole game of, the whole yoga of managing all the terms at the same time. Sure. Yeah, I remember.
Yeah, apparently, you should buy the book. His grandkids do have college costs coming up, you see. Any other questions?
What do you call the signature of L?
So this is, if you tensor L with R over Q, you get a bunch of copies of R and C. You get this many copies of R, this many copies of C.
Any?
So I have a general question. So the following thing: given an interval, is it are there some estimates of the number of
Yes,
arithmetic subgroups with covolume in this interval?
I think so. There is work. I have to remember. Let me not say any names to not make wrong attributions, but there have been some work on counting lattices of covolume, at least below a certain bound. So maybe not in an interval, but below a certain bound and how this grows in terms of this bound. This has been studied by Misha and some Misha Bilar-Lipetsky and some collaborators. So
okay,
yes.
For all semi-simple.
You'd have to look at the paper to get the exact.
Okay, there is.
I think yes, but I'm not sure exactly how general. If it's split or what. I think it's fairly general. I think they have some general bound, and they did this namely because so it's a bit inspired and related to subgroup growth for lattices. So it's these things are kind of intertwined, right? Because if I give you a lattice and you take a finite index subgroup, well, you know how the volume of the finite index subgroup grows. It's exactly growing by the index. So this, yeah. So it's when they were studying all these kinds of questions that this popped up.
Okay, thank you.
Of course.
Any other questions? Let's thank François again.
Thanks.
Thank you, Brad, for sharing the session. We'll have a break in 12 o'clock.
I think that's right, but I didn't want to make any, yeah.